Yeah, I'm very happy to be here. I made it on time. Yeah, that's good. So my field is actually computational fluid dynamics, and probably like all the other fields that you're probably working in, probably also fluid mechanics, you know that AI has penetrated a lot of the disciplines, yeah, and I want to talk today a little bit about what we've been doing in this respect. Yeah, so this motivated us very much to integrate AI technologies into our computational fluid dynamics simulations and to learn from the big data that we're producing. So I'm going to provide today a little bit of an overview what we are doing in our group. So, but first, let me talk a little bit about high-performance computing itself. Yeah, you know, you're very much aware that we are nowadays facing a lot of different architectures in the HPC systems. Yeah, so we're talking really about modular supercomputing architectures, as you can see it here on the. Oh, it's not working. Okay, sorry. As you can see it here on the, oh no, you cannot, okay. But as you can see it here on the right side, yeah, so we have really different components nowadays in our HPC systems, yeah, that we're talking about a cluster module which might be comprised of CPU-based system, a booster module with GPUs equipped, data analytics module with FPGAs, for example, to process streaming data, neuromorphic modules is something that we're working on at the Jülich Supercomputing Centre at the moment. And quantum modules that we're integrating also in our HPC landscape for optimization problems. And of course, in the background, you have this multi-tier storage system. And you can look at these kind of things from two perspectives, of course. Yeah, on the one hand side, from the user perspective, you're always interested in obtaining as fast as possible a solution. Yeah, so you're looking at finding the most suitable hardware for a specific task, and the tasks, they grow more and more complex. Yeah, you have nowadays multi-physics simulations, different components of your simulation that might run better on a certain module of the module supercomputing architecture. Yeah, so you can imagine that you have running a CFD simulation on a CPU partition, and at the same time want to do learning in situ and move the data to a GPU partition and train an AI with that. Yeah, so you are very much interested also in enabling these intertwined AI and HPC workflows, and of course you want to do performance engineering of your code and understand how to improve the performance of your code. And with this, also scale across the machines that we see nowadays. On the other side, you have the HPC side, the center's perspective. Yeah, of course, the HPC machines should be should allow for a huge diversity of applications, and of course, it should be possible to share the resources effectively. And this is something that we integrate also in our exascale system that we just in September inaugurated. Yeah, Jupyter is the name. You probably all heard of it. Yeah, it's co-funded by EuroHPC with 250 million euros, and the other 250 million euros come from Germany, 125 million euros from the government itself, and 125 from the state of North Rhine-Westphalia. And you see, it also has these different kind of components that we want to integrate into the system. The working horse is actually the booster module, yeah, which is with 1 exaflop. Yeah, just recently we gained number 4 in the top 500, but we are also looking at interactive supercomputing with visualization. We are integrating very soon also a universal cluster based on an EU technology. The quantum module you see again, neuromorphic modules, and any future systems as well. There's a placeholder for that. Yeah, just some specs about this thing. Yeah, it's the Jupyter machine, the booster. Yeah, the working house that I'm talking about is a Grace Hopper architecture, yeah, from NVIDIA. We have 6,000 nodes installed, yeah, approximately. So some nodes are still being installed at the moment. We have 4 chips per compute node, and here on the right side you see a little bit the architecture of the chip itself. On the left side you have the Grace CPU, which is an ARM-based system, very energy efficient, and on the right side you have the Hopper GPU. CPU for number crunching, and yeah, it says small or equal 512 gigabytes for the CPU part. Here we have actually installed 120 gigabytes LPDDR RAM, and on the Hopper side you have this high bandwidth memory of 96 gigabytes, and of course you have with the NVLink, the latest version, also a very fast interconnect to the other GPUs and also to the network. Yeah, it's a Bull-Sequana system, directly cooled blades, and there are 2 compute nodes per blade. Okay, so, but I don't want to talk too much about hardware. Yeah, so what we are interested in is running simulations efficiently and making use of AI for that. Yeah, so you can imagine that you have very expensive simulations that you want to run, computational fluid dynamics simulations with looking at more and more fine-grained simulations are very expensive. Yeah, so if you're looking at direct numerical simulations or large-eddy simulations where you model a certain part of the fluid mechanics, they can become very expensive to run on the system. And with the appearance of AI, we are very much interested in how we can improve the performance, maybe the prediction performance, integrate models into the simulation codes that we have. How can we reduce the energy consumption by that, by going faster to a solution that we're interested in. We're looking at the performance itself. Yeah, so I want to talk today a little bit about the convergence of this CFD and AI, how we look at that and what we do with that. And I brought just 3 models. There are many more models we can talk about, yeah, but I just want to bring 3 examples that we've been recently working on. One of them is the transformers that we use for time step prediction in CFD simulations, autoencoders to do predictions for simulations that we are not able to run, but we had training data for simulations that we run before, and diffusion models for, let's say, subgrid scale modeling or wall-resolved large-eddy simulations. Okay, so but before I talk about the AI topic, I want to talk a little bit about the CFD code itself that we're using. It's called Maya, and Maya stands for Multiphysics Aerodynamisches Institut Aachen. It's a mixture of English and German, but from that you can probably already guess where it's mainly developed. Yeah, it's developed at the Institute of Aerodynamics, yeah, that's the English version, at RWTH Aachen University, and it has been developed already for a very long time. Me as a PhD student back in 2009 working on that already, and even before. It's an open source CFD software. Yeah, it's a research software, multi-physics simulation code. It's jointly developed together with us at the Jülich Supercomputing Centre, and we have really a lot of lines of codes in there. Yeah, almost 400,000 lines of codes, and many people are working on that. Yeah, so many PhD students are working on that, and we collaborate with the PhD students and with the scientists at the RWTH Aachen University. It's mainly C, C++, and we have different parallelization strategies. Yeah, so we do MPI, OpenMP for shared memory parallelization. We use the parallel SDL, which is available in the C++ standard since 2017 for bringing the code to NVIDIA GPUs, but there's currently also developments going on to port this to HIP, to the AMD GPUs, and of course we're also doing parallel I/O. Yeah, with that it wouldn't be possible to really do science anymore. And yeah, I brought some examples here. Yeah, so we're doing a mixture of things with that. Yeah, so I come from the field of respiratory flows. This is what you see here on the right side. But there's also things like technical applications, propeller flow, air acoustics. We're simulating by coupling, finite volume, and discontinuous Galerkin, and fully resolved particle simulations. So most of the time we're using hierarchical Cartesian meshes with dynamic load balancing and all of these kind of things which make writing code quite complex. This is a more general overview of the software. You see that we have a parallel grid generator. Yeah, you usually start with a geometry, yeah, that you would put in, that you want to compute the flow around or inside, let's say, and then you have, let's say, a structured mesh that you want to generate, or this hierarchical unstructured Cartesian mesh that we're looking at. And we've been writing a code that does this grid generation in parallel. Yeah, you can generate billions of cells for your computation in just a few seconds. milliseconds on HPC systems. Then you have really different components to do your flow solution. Yeah, so lattice-Boltzmann solvers we have in there. That's mainly for weakly compressible flows. We have a discontinuous Galerkin. I already mentioned that, to do the acoustic simulations. We solve the acoustic perturbation equations for that. We have a finite volume method for compressible flows, a level set solver to track surfaces within, for moving boundaries within the simulation, and a Lagrangian particle tracking tool. And all these kind of things can be coupled. Yeah? So you can couple the level set to finite volume, the level set to lattice-Boltzmann, the Lagrangian with the lattice-Boltzmann solver, etc. Yeah? And this is also what you see then here on the top right corner. Yeah? So we, in this hierarchical Cartesian meshes, we can assign different solution methods to different or the same number of cells that we have in the computation. Yeah? You can, for this example where you have this hierarchy, yeah, it's an octree basically, you can have finite volume cells, level set cells, but also mixtures of finite volume and level set, or finite volume and particle tracking cells. And this way we know the weights basically, and you can do also do dynamic load balancing on that. I brought some scaling plots here. Yeah? So what you see here is on the left side top, a coupled finite volume discontinuous Galerkin for air acoustics simulation, which ran on various systems of Euro HPC. Yes, from Vega to Carolina, and the Hawk system is the old system at HLR Stuttgart. So these are a number of nodes going up to 4,000 nodes, as you see, doing quite a good scaling. And here is a comparison down here of a coupled finite volume particle solver, also on the Hawk machine, with more than 11 million particles and over 1 billion cells. And the distinction between the two cases is here we can do interleaved computation between the two solvers, saving some time and avoiding idling of the different solvers. But there's also the lattice-Boltzmann code, as you can see. These are a little bit older scaling plots, but you can see that we scaled up to 250,000 of course already on the UQueen system that we had at Jülich some years back. And here are some newer plots here on the Jedi Jupiter system, yeah, for the lattice-Boltzmann code going up to 32 nodes, and the Joules booster is or was the current working horse on the German side that is still in operation. Okay, so now let me move on to AI for CFD applications. And as I mentioned, I want to talk about, let's say, autoencoders a little bit, transformers, and diffusion models. Yeah, so let me show you this example here that we used mainly data from for our training. Yeah, so it's the simulation, a large-eddy simulation of a turbulent boundary layer. And the idea here is to introduce active drag reduction. And what does it mean? If you look a little bit closer, you see that there are some waves traveling, and these are spanwise traveling waves, yeah, and with these waves we want to influence the boundary layer and reduce the drag. The idea is, of course, to, on the one hand side, drag reduction, and with that also obtain power savings, energy savings, and in total, because you also need to invest energy to do these movements, you're looking at net power savings. Yeah, so what you can see here on the right in the corner is basically the drag coefficient. Yeah, the black line is basically the one if you don't do any active drag reduction, and the white line you see if we do activation of this active drag reduction technique, we are actually able to reduce the drag in the system. So you can look at that from a short or middle term. Yeah, of course, this is a technique that still needs to be understood. Yeah, the fluid mechanics behind that. So we are very much interested in how this is working. We want to reduce the simulation costs with machine learning, for example, and of course also optimize the design choices. Long term, the idea would be that this goes into application, yeah, into flight, yeah, for cruise flight, or into high-speed trains. And of course, these kind of simulations, also the training, because there's a lot of data that we're producing, requires HPC resources. So just a little bit of background, you could also imagine doing drag reduction passively. Yeah, this is what is shown on the right side. Then one of the examples is riplet surfaces. Yeah, so you can imagine like a shark skin, so that you have little bumps basically on the surface that influence the boundary layer behavior, and hence also the drag. On the left side you have an active drag reduction where you invest energy, and you have of course certain advantages and disadvantages. Yeah, so when you have something mounted directly and you cannot move it, like this passive drag reduction, then it's of course only tailored for this specific flow condition. And with that, if you look at the span of different flow conditions that you would have for an airfoil, you have in some, of course, a lower drag reduction and also less net power savings. But on the other side, you don't need to move anything. You don't need to invest any energy. On the other side, if you look at the active drag reduction, you can flexibly adapt it to your flow conditions, and with this you can obtain higher drag reduction and power net savings. But on the other side, you need to invest the energy, and it's at an early stage, let's say, compared to the riplet surface, which just need to be mounted. Let's say this has a medium technology readiness level. So we are very much interested in the fundamental fluid mechanics of the case on the left side. And therefore, you saw the waves that were shown on the wing section. This is also what is shown basically here. So what we investigated is here this case. You have incoming flow, which is synthetically with synthetic turbulence that we apply at the inlet boundary conditions. We have a wavy wall. We move the wall basically to modify the boundary layer, and we have, of course, periodic boundary conditions. And what we modify is, in total, you see there are 88 configurations that we actually ran and obtained quite a huge amount of data. 8.3 terabytes that we actually also use then for the AI training. So, but we are looking at modifying the amplitude, the wavelength, and the period, basically. These are the parameters that we're looking at. So in general, these flow solutions were run with a finite volume method. I was mentioning that. And as you can see here, we solved the Navier-Stokes equations. We have the awesome method for the inviscid fluxes and for the reconstruction on the cell surfaces. For the flow quantities, we have a muscle seam for the time integration, for the temporal integration, a 5-stage Runge-Kutta scheme, all of second order accuracy, and we have a Miles approach that basically allows us to mimic the viscous dissipation by the numerical dissipation that we obtain with a lower grid resolution. It's a structured body-fitted mesh, and it's an arbitrary Lagrangian-Eulerian approach, which allows us basically to modify the surface and at the same time also the mesh structure. The simulations were run at a Reynolds number based on the momentum thickness theta of 1000 and at a Mach number of 0.1, so almost incompressible. So this brings me a little bit to the autoencoder idea. So what we wanted to do initially, we wanted to, because these data are quite large, these 8.3 terabytes, we wanted to have a smaller representation, have a compression of that, and for that we implemented an autoencoder, which is shown basically here on the left side. This is it's a U-net-shaped architecture. We basically put the velocity fields in, and we do compression to a latent space, which is then this Z. I hope you can see that. And then we can do the reconstruction from that again. So we train basically the latent space and do, let's say, a loss calculation based on the inputs that we provide to the training. And this is then concatenated because in the end we are not only interested in compressing the data and decompressing the data, but we also want to obtain for certain flow conditions, like I said, with the different wave numbers and with the amplitude, etc., also an understanding what's the impact on the drag coefficient and the power net savings. So we trained a second network, what you can see here on the right side, and there we actually feed here in one of the last steps. We concatenate basically the parameters of the simulation into the architecture, which is then the amplitude, the wavelength, and the period of the wave basically. And we trained this network and wanted to see if we can do predictions of unsimulated cases. So looking a little bit at the performance. So first of all, of the first part, of the reconstruction part, so compression, decompression. You see here on the left side qualitative images of the streamwise velocity, and on the right side of the spanwise velocity. And what you can see is that is hardly distinguishable from a, let's say, from a qualitative point of view. but nevertheless we also wanted to have a more in-depth look at the quantitative measurements, and therefore we made use of this noise-assisted multivariate empirical mode decomposition tool that was also developed by at the Institute, which provides us with so-called intrinsic mode functions, and an intrinsic mode function is a representation, a modal representation of a certain range of scales. So you can imagine that the first mode here, IMF1, represents basic small scales, yeah, and going up to IMF5 that we looked at, where we're looking at bigger scales, yeah, and qualitatively you already see that the IMF for the reconstruction, which is the one on the right side, is less accurate, but for the IMF5 you already have a quite good agreement, and we also looked at that from a power spectral point of view. You see here below plots for the IMF1, so where we're not doing so good, but for the IMF5 we already have a quite good agreement. So this is for the reconstruction part. The second part is the prediction network, and there we of course have to look at interpolation, because we are covering a certain range of parameters for these wavelengths, etc. And we also need to look at extrapolation, if we look beyond what we have simulated. And you can see here that at least for the interpolation that we get quite a good result for the drag, which is the upper part. We're looking here at the mean results, and for the power net savings we're also doing okay-ish, I would say. But if we look at the extrapolation, then you can see for the drag reduction it's again quite good, but then we are pretty off for the net power savings prediction. So this is something that we're still looking into, and the idea is here really on top of what you have seen, like this plain autoencoder with the attached prediction network, to also integrate physical information into that. Okay, this brings me to the second architecture I wanted to talk about, which is transformers. So transformers you all know probably from ChatGPT, from large language models. So the idea is here, of course, to give it a certain sentence, and basically it does a reconstruction of an answer with the help of probabilities that it has learned from. So it will provide you with an answer based on some information that are stored in the mesh with probabilities. So here the idea is pretty similar. So this stems actually from the original Attention is All You Need paper. We took that and wanted to apply that for fluid mechanics. So, but the thing is here, we didn't want to predict the next word. What we wanted to do is we wanted to predict the next time step in a fluid mechanics simulation. So we have a set of temporal resolved simulation and time steps, and we feed that for the training. This is this UT1 until UTM, and of course you have the usual layers in your transformer, so some input layers, positional encoding, you word to vec basically to do the encoding in numbers, and your tokenization, etc. And the most important part is probably what you have in the encoder layers. You know that there is some kind of attention layer where you basically describe how relevant or how close certain words are usually to each other. But we do this here basically for continuous time steps in a fluid mechanics simulation. And then of course in the feed-forward neural network you have a nonlinearity basically to learn from the information that you gathered. And you have several of these encoder layers. The architecture is similar, so to the Attention is All You Need paper, 6 encoder layers, and then you feed basically things that you have learned in the encoder also in the decoder for every decoding part. And the idea is here really that you provide it with a different set of time steps, and then you get one additional time step. You see the last time step that you provide here at the decoder part would be UTN-1, and you would continue through that, and in the end you would have a UTN, a prediction of your next time step. And the idea for that is really to avoid sometimes, where it's possible, expensive simulation steps. So you would run an LES simulation, and then have the transformer predict 1 or 2 time steps, and save basically these 1 or 2 simulation time steps. Here's the loss function, which is basically based on the direct difference between the velocity fields, but also based on the difference in the gradients. Okay, so let's have a look at some results of that. Yeah, you see here again a turbulent field on the bottom. Yeah, for different time steps from left to right, you see for a time step prediction of 1, time step prediction of 2, time step prediction of 5, and then 10. And then we plotted basically the original field against the predicted field. So we also did the simulation because we wanted to know, is this true, what we're getting from the transformer prediction? And we plotted this along the line here. Yeah? So the red dashed line is from the prediction, the black line is from the original, what we would expect, the target configuration. And you see that for 1 time step looking ahead, the error is quite small, for 2 as well. When we move to 5 time steps, we are already obtaining a higher error, as you can see, and for 10, we are already quite off. So the idea would be then really to say, based on this information, do maybe 1 or 2 time steps with the transformer. And this is also plotted here again on the left side. Yeah, you see basically the model accuracy for the time steps. Yeah, number of time steps is on the bottom. Yeah, and the blue line is the mean squared error of the meters per second squared. And what you see is that with a future, looking way more into the future, your error increases. Yeah, but stays quite small for 1 or 2 time steps, as you can see. Same with the R2 score. Yeah, telling you a little bit about the robustness of the model. Yeah, it's decreasing. Yeah, but the important thing is what you see here at the bottom. Yeah, if you do a time step for an LES computation, and we measured that for this specific configuration, you're almost at 40 seconds. Yeah, node seconds. Yeah, but if you do the inference of the transformer, you are a little bit more than 50 times faster with that. Yeah? So if you have really a trained model, you can do really accelerate your computations with that. Same is valid for the memory. Yeah? You see you have quite a lot of memory requirements for the LES computation, but for the inference, what you do, it's way less memory. Yeah? So you almost have a factor of 1,100. And here on the right side, we also wanted to look from a physics point of view also into that. We did some dynamic mode decomposition also of the predictions for, this is shown now for 2 time steps. Yeah? This is the first mode comparison for the different velocity components, u, v, w, pointing in the different x, y, z directions. And you see basically that these plots, they match quite well. Okay, the third thing I wanted to talk about is convolutional defiltering models. And the idea here would be to use this kind of method for subgrid scale modeling. So in areas where maybe you have an under-resolved mesh in your large-eddy simulation, and specifically also in the vicinity of the walls. Yeah? So usually you're very much interested in, let's say, the drag computation, and therefore you need to be very accurate in the vicinity of the wall to compute the wall shear stresses, etc. So usually you would need a very high resolution. Yeah? And looking at the flight conditions, in-flight conditions, you cannot do a direct numerical simulation. This is just too expensive. Yeah? You could probably not do this even with zeta-scale computing. Yeah? So what we want to do is to find a model, yeah, and we want to base this here on the convolutional defiltering method, yeah, which is based on these diffusion models. I will talk about that. To find, prescribe information in the vicinity of the walls or in regions which are under-resolved. So the idea behind this is, for the diffusion models, is that you have a forward process and a backward process, and these are Markov chain processes. You look at, let's say, an image, yeah, a clear image of this person there, and basically you have a forward process that moves to a very noisy image at the end, yeah, which is on the left. And this Markov chains, every element or every time step that you make basically only depends on the information that you have in your last node. That means for this forward process, yeah, that we call here Q, you have your Qt that you want to calculate given you Qt minus 1. So you have the information from the node before to do basically an update of your current node, yeah, of Qt. And what are we doing here? We're continuously applying Gaussian noise. Yeah, this is basically shown here with this n equation there on the left side with mean and standard deviation, and if you basically concatenate all these different steps, yeah, from the initial image x0 to your final image xt, it's nothing else than a convolution. So basically you can use this and explain this also as a product. And the idea is basically with this Gaussian noise, yeah, and this is plotted here as an example. You would start, let's say, with a very easily seen, let's say it's an image, and later on we are also using images of the fluid velocities, yeah, with some pixel information here, and basically you project that into a three-dimensional space where you also have probability density as your third information, and then you would basically put your Gaussian distribution on top of that and sample within this Gaussian distribution. Yeah, so you would have a higher probability, of course, in the region of the mean, and the further you go outside, you have a lower probability of sampling. And in the end, you would pick a sample here, yeah, which is the yellow one, and then you update basically your information. Yeah, and this is then what comes out of that. So the question is now, how does this help to generate, let's say, the missing information? So the idea is here to go the same process backwards. Yeah? So you start basically by a completely noisy image, and you want to reconstruct an image. Yeah? So this is commonly used in generating artificial networks. Yeah? So, and what people usually do is to use a unit for that. Yeah? So they want to have a unit that learns basically the reconstruction of the noisy image towards the original image. Yeah, and as you can see here, we had this process here, this green one. Yeah, this was the forward process in green going to xt. Yeah, and we want to have this inverse process p theta, and theta are actually the parameters that you have in your neural network. Yeah, that describes you the backward process. So what we want to do, considering as a loss, we want to minimize the negative log likelihood for that. And of course, yeah, similar like before, this is also a Markov chain described in the other way around. Yeah, so you can describe your information. Your reconstruction depends only on the last step again, and you can also write this as a product again, as you shown here in the right corner. So a little bit of math. Yeah, so if you do the calculation, so we're interested how to formulate the loss basically. For that. Yeah, so you can rewrite your negative log likelihood basically as an integral formulation. The problem is here you would need to integrate over all possible paths. Yeah, so I've shown on the last slide like one path that goes back. Yeah, the red one here. Yeah, but there are many paths. Yeah, you don't know which path is the correct one. There are many paths. Yeah, infinitely many, and you cannot actually calculate this this integral. Yeah, but what you can do is expand again, multiply and subdivide by your backward process and move that then basically out, and then reformulate it as an expected value. Yeah, and therefore you make use of this Jensen's inequality. Yeah, and you end up with this so-called evidence lower bound. Then between this step and the next longer step this here, there are many mathematical steps in between. Yeah, if you're interested, you can have a look at the paper number 13. But what you end up with is this expression here, and you have KL divergences here, and KL divergences, they are measurements of the distance basically of probability distribution functions. So how far are probability distribution functions away from each other. So what you want to do is for a forward process and for the backward process, align these probability distribution functions that you have. So if you look at the first term, that one vanishes, yeah, because there's no dependence of theta, and we are interested in this theta, yeah, because this is part of the unit that we want to do. And the last part is small because it's only one step. Yeah, it's just describing the last step from the almost final clear image to the clearest image. Yeah, so this is also something that we can neglect there. What remains is this part here in the middle. The thing is here, you have the true posterior in here, x0. Yeah, so you can reconstruct the information, of course, if you know what the picture looks like. If you don't know how it looks like, then you have a problem, of course. Yeah, so in general, we don't know how the picture looks like. So this poses a problem here, and but we can make a trick here. The idea is here, for both of these things, yeah, for the forward and for the backward process, we know that they are Gaussian processes. So they have some some Gaussian information in there, yeah, and what we do is we fix the standard deviation and are then just interested, and this is shown what is here, yeah, so one of them is for the forward process and the other one is for the backward process, yeah, on the right side, top. What you want to do is you want to minimize basically the distance between the means, yeah, so you have these two curves basically and you want to minimize the distance, and this can be then expressed in the loss, yeah, because then you're talking about this mu t and mu theta, yeah, as a difference between these two informations for every step that you make in the chain, yeah, and this is what you want to minimize. So ideally, when you have your loss considered, yeah, in your UNet, you want the loss to be 0, yeah, you want to reduce the loss, so this is something that you can use. You can do some parameterization to express this also as a noise difference, as shown here, and then implement this in your neural network. But there are also other methods, let's say, that you could be used, physics-based, etc. So I said we want to do this also for fluid mechanics. Yeah? So what we did here, we started with an initial image and we did the filtering. So we continuously applied Gaussian noise and we ended up with a filtered image which doesn't really look like anymore like the original one. It's just a very, very coarse approximation. And the process is in principle the same as I described. We have a forward process, we do Gaussian smoothing, yeah, and on top of that have a small noise that we additionally add because we also want to have not a bias, introduce a bias due to the step size of the Gaussian that we introduce. Yeah, so we end up basically with some kind of very much filtered image, which is not the original one anymore. Then we train this three-dimensional UNet and move that back to our original space, yeah, to get the reconstruction. Yeah, so the output is then really the defiltered element, which is shown here as Z tilde, yeah, and it should be an approximation of the original flow field that we coarsened with that. Okay, let's have a look also again at some results. Yeah, so you see this here for different velocity components. Yeah, on the one hand side it's the U component, and here is the gradient on the right side, and again like a cutting line through that. And what you see is basically the original one, which is the dotted black one, which coincides very well with the output of the reconstruction. Yeah, and the filtered one that you see is very smooth and not very aligning very well. So this is actually here at an error of 0.5 for the velocity component, and for the gradient we have a little bit of a bigger error. So here then on the left side also some power spectral density analysis. Yeah, you see here the black line and the blue line, they coincide very well. Yeah, this is from the reconstruction, and the idea is then really for the wall resolved LAS for the wall modeling, really to have a coarse mesh in the vicinity of the wall and then do some kind of interpolation, and then use this technique specifically, the CDM, to reconstruct the information in the vicinity of the wall, and use this then for your, let's say, wall shear stress calculation, and then later on for the drag computation. So this is still work in progress, I would say. Okay, I have a few more minutes, so I also want to talk a little bit how we run the AI efficiently at scale on HPC systems. This is mainly for training. Yeah, so all the problems that we usually consider are data parallel problems. Yeah, so we usually have a lot of data, but the architectures we're looking at are rather small. There's also, of course, the possibility to use model parallelism if you have like very huge neural networks and you want to distribute them across the HPC system. But in data parallelism, basically every worker, every GPU has a copy of your neural network and does the training on a separate data set. Yeah? So you have usually a mini batch, and then you divide this in micro batches, as you can see it here on the right side, and then of course information needs to be exchanged. So there's usually like one host entity which collects the information about the gradients and gives then the information to the workers to update their weights, basically. Okay, so you want to use as many GPUs as possible, but at the same time you want to fill up all the GPUs. You want to use, let's say, 1,000 GPUs, yeah, and you want to go to 6,000 GPUs or so, but you still want to fill up all the GPUs. That means you also would need to provide it with more data. And if you would provide it more data, you also increase the batch size. And with the batch size, you also have then a less frequent update of your model parameters. So you actually decrease the performance of the model, of the training. So The idea is really to look at where the sweet spot is for the number of GPUs. You can steer this a little bit with different learning rates, yeah, so how far you go in your optimization space, yeah, so you can do this parameter-wise. There are different strategies, just as an example here, there's this cosine annealing we played around with, or an exponential case for adapting the learning rate. But there is also more that you can do. Yeah, so you can use adaptive learning rate mechanism. One optimization method that makes use of that is the Atom optimizer. I recommend using this for most of the problems that you have. But you have also ADA sum. Yeah, so usually if you look at different workers, they would probably for a certain parameter predict a different direction, yeah, to go in your optimization space. Yeah, and then you can make use of ADA sum, which helps you basically to align these different solutions that you obtain. Yeah, so if you have almost parallel results, directions in your optimization space where you want to go, then of course if you just would add the two vectors, let's say, then you would end up with a very long vector. Yeah, maybe you're overshooting your solution. Then you would rather take half of this information, which is good, yeah, which would be good. Then on the other side, if the vectors are orthogonal, yeah, then you can probably just simply add them. But if they're neither parallel nor orthogonal, you would need another solution. And what helps here is projecting one of the vectors to the other one and scale it especially. Yeah, so this is basically shown by the formula here below. Another thing is automatic mixed precision. So you can do your training at different accuracies. Yeah, what is important is that your loss is calculated correctly, because you want to be as close as possible to your solution, to your reference solution. But you could do a compute of your forward pass in FP16 accuracy, and then compute the loss in FP32, and then you get your loss, and then you might want to need to scale, because you don't want to have the loss to be too small. Yeah, when you represent it again in FP16, so you scale it with a certain parameter. Then you do your backward pass again, yeah, to update also your model parameters. You can also do this then in FP16, but then you also need to check if you have like not a number or infinite, if you divide by 0 or things like that. And if this is not the case, then you update basically your gradient, you unscale your gradient, and you update your optimizer. So there is more you could use. QDNN, this is something that's implemented by NVIDIA. Yeah, is basically a library that you can make use of, and it runs different kernels at the very beginning as benchmarking, and selects basically the best kernel for your problem. So I really recommend looking at that. Another thing is gradient accumulation. Yeah, so maybe you not always need to communicate the gradients all the time. So this is this algorithm basically collects the information of several of these steps, accumulates them in the so-called bucket, and then uses one single parallel operation to fuse all the elements. And this is also good because this is, uses asynchronous communication. Another thing, of course, yeah, because we have it in the hardware, is using CUDA-aware MPI. Yeah, and on the other side, what we played a little bit around with, but in another project was also with DALI, that's also an NVIDIA library, to efficiently load data directly into the GPU, yeah, for I/O. And as you can see, this is from the website of DALI. Yeah, you see that at least for these different kind of learning frameworks, that you get an improvement here, yeah, with the throughputs in images per second. So let's look at some results where we took the autoencoder, yeah, so this compression network, and we wanted to understand what's the impact on the performance. And actually, with the automatic mixed precision, applying QDNN, the gradient accumulation, the CUDA-aware MPI, we were able to do improvements by 90%. Yeah, so this is what you see on the left side. Yeah, the standard one is the what you would usually do. Yeah, and if you apply this optimization, this is a logarithmic plot, as you can see. Yeah, the blue line is basically what you obtain from that, and then you also see some scalings there and the efficiency. But on top of that, we also played around with this bigger data set that I was talking about, this 8.3 terabytes, and I wanted to see how good the scaling of this thing is. Yeah, so we did a training scaling analysis on the almost whole Joules booster system. Yeah, so the Joules booster has roughly 4,000. Yeah, some of the nodes were not available at that time, but we end up with a computation efficiency of almost 96% here. I don't want to talk too much about hyperparameter optimization, yeah, because Eric from CERN, he's talking this afternoon about that. Yeah, so just a glimpse. Yeah, so you can tune a lot of hyperparameters, of course, in your training, and have different trial runs and see what hyperparameters yields you the most accurate model in the shortest amount of time. Yeah, we've been inventing a new algorithm for that. So usually you can do this asynchronously. Yeah, this is what the asynchronous successive halvening does. Yeah, ASHA, and here on top we have Rasta. Yeah, this is a newly invented algorithm which basically takes available resources when they become available again, when some trial has stopped, that can be assigned to additional runs and make them basically faster. Okay, this brings me to my summary conclusions, ongoing work. Yeah, so I said this in the very beginning. Yeah, there are really a lot of models around. Yeah, so I have not touched physics-informed neural networks or physics-constrained autoencoders, all these kind of things. So we are also working on that. But this was just an excerpt of the different models that we are working on, specifically for this turbulent boundary layer case. Yeah, we are also working on reinforcement learning for shape optimization, for example, to optimize nasal cavity flows. Yeah, to provide surgeons with some input for surgery suggestion. Yeah, so there is a lot of things going on, and the thing is, you always need to look really very carefully what kind of model is very much suited for your specific problem, yeah, and for your data that you have. And then you need to look at the hyperparameters as well. Yeah, so I just said here, okay, I didn't talk about it, but you can compare physics-informed neural networks and deep neural networks directly. Yeah, for predictions of flow fields, let's say. If you want to train a network fast, for example, you would do DNNs. If you don't want to spend more computational effort, you could use pins. Yeah, but at the same time, you might get a better prediction because the pin also knows some more about the physics of your flow field. And the same with physics-constrained autoencoders. You also can include physics into that. In the end, yeah, it's a matter of how much resources you have at hand, how much data you have at hand, what your problem is. If you want to do hyperparameter optimization and things like that. But things that we are currently looking in, and this is something that I mentioned in the very beginning, where you really have this hybrid workflows with running on different partitions of your HPC system, is running a simulation at the same time dumping the data. But because in the end, you will not be able to process all the data when it's once written to disk. Yeah? So you have these simulations, and during the simulation you have the information at every time step. Yeah? So you could process basically for an AI training information at every time step, and writing all the information to disk is simply not feasible. The same that we see nowadays with data analysis in general, yeah, or with visualization. If you really run these large-scale simulations, you cannot do that anymore on the data that you stored on your disks. Yeah. Hyperparameter optimization for model tuning. Yeah, so we're looking into a tool that we are developing also together with Eric, yeah, with CERN people, which is iTwin AI. It's an MLOps pipeline for digital twins, and this continues to be developed and extended for further applications. So we want to make use of that. The idea here is really to abstract the complexity of HPC from the, let's say, novice user of HPC systems, or the novice person that wants to run AI training on HPC systems. And we are integrating also the different models that we already obtained. Yeah, they're part of an open source library, AI for HPC, that is available. You can have a look at that. There you find information on how to train the models, where you find the data, etc. So with this, I think I would finish. Yeah, so here are some reference for you, and would be open for questions. Thank you very much for your attention.